then can't you just cut a big square out? Well, the problem with this is you're not cutting just one, you're not cutting one square out. You have to cut 4 squares out. And so if you have to cut 4 squares out, then the biggest we can do is basically half of that length, which is where we get 3 over 2. So what I have now is the smallest x can be is 0, the biggest x can be is 3 over 2. And that's inclusive. Now, here is this is what the AP exam expects you to do. To establish something as a maximum or a minimum, what they expect to see. I expect to see all this work where you actually found out, in this problem we found out that our critical values are at, we found our critical values at 3 over 2 and 1/2. We also know that our domain is from 0 to 3 over 2. And what College Board expects to see to verify that something's a maximum or a minimum is they expect to see a chart. And on that chart, they're going to have x. This is how big x can be. This is your volume. And you're going to plug in your endpoints. You're going to plug in 0 and 3 over 2. And then you're also going to plug in your critical value, which in this case, your other critical value, which is 1/2. This has to do with with the extreme volume theorem that we did at the beginning of the chapter with curve sketching. Remember, if you've got an interval, how do what's the absolute max and absolute min? Your absolute max or min could occur at an endpoint, so you have to check those. Unfortunately, if you plug things back into the factored form, it's not as bad. If you plug things in here, it looks a little intimidating. But if you plug 0 here, well, 0 times all that stuff is 0. If you plug 3 over 2 in, well, 3 over 2 times 2 is 3, so 3 minus 3 is 0, so this gives me 0. And then when we plug 1/2 in, we already found that answer is 2. And so this chart is the verification that 2 is the absolute maximum. And as silly as it sounds, this is what they expect. Now, as far when there are not many optimization problems that I can give you this semester. There are some optimization problems that we'll talk about next semester. But when we do that, I'm going to really emphasize draw the chart, draw the chart, draw the chart. All right, so that is the open box problem. Right. Next, I'll have to have the partner to this open box problem. And the partner to this open box problem, it's still an open box problem, but the wording's a little different. So for this one, it starts off, let's see, what do we have? It says a box with a square base and open top must have a volume of 32,000 square centimeters. Find the dimensions of the box that minimize the amount of material used. Oh, something that's not terribly important to you, but it is kind of interesting from the teacher's perspective. Every textbook has an open box problem. They typically have one in the examples, so that's one of the key examples that they use to teach. They always have one in the exercises. And what I've noticed is the numbers are always the same. Like this was a box that we had a square sheet of paper that was the length was 3. Sometimes they have a rectangle where one side's longer than the other, and the numbers don't change. Like I've got 15 different calculus books. They're all the same numbers. And then a couple of years ago I tried to write a question. Turns out if you don't pick the dimensions of that square just right, the numbers are hideous. Like for this problem, when we took the derivative of this thing, and to get something that actually factors, when you have rectangles, I think there are only 2 or 3 rectangles different rectangles that show up. If you pick any of those, if you pick anything that's not those, it doesn't work. All right. Anyway, back to problem 10. So it talks about a box. All right, fine. With a square base and open top, must have a volume of 32,000 square centimeters. Find the dimensions that minimize the amount of material used. Step 1 talks about a box. Draw a box. So when we draw our box, here's our, I'm not very great at drawing boxes, but whenever you have these, they are boxes. Now they tell us some things about this box. They tell us it's a square base. And since they tell us it's a square base, that means this length and this length have to be the same. So I'll call these x, and then I don't know what the height is, so I'll call it h. Now I've drawn the picture, I've labeled the picture, now the fun begins. What are you trying to optimize?
Surface area?
Surface area, right? It tells us that, right? It says, find the dimensions of the box with the to minimize the amount of material used, all right? Fancy name for surface area. So we're trying to minimize surface area. So I'm going to write down SA, and now I need to write my equation for surface area, basically the amount of material I'm using. And so when I look at this, well, let's see the bottom, that's a square. So it's x times x, that's going to give me x squared. If I look at the sides, well, this side is x times h, so this side is 1xh. And let's see, this is another h, so the area of this side is also an xh. The area of this side to the left is also xh, and the area of the thing on the back is xh. So I end up with the amount of material I'm using is the base plus those four sides, which is going to give me 4xh. Notice I didn't have the top because it's an open top. Sometimes they're tricky, or they try to tweak it a little bit and say it's got a closed top, and they sometimes make this picture a little uglier than it is. But for the most part, that's it. All right, so this is what we're trying to optimize, what's minimize the amount of material used. This is what I'm going to take the derivative of, right? I'm going to take the derivative of this, set it equal to 0, do all of my fun things, right, that I, do all the calculus stuff, right? But I can't do any of that because, right, I've got two variables, right? I can't deal with two variables, so I need a helper equation. And so now when I look for my helper equation, right, what's the number in the problem I haven't used?
$32,000.
32,000. That's the only other number I have, right? So let's see. So I'm going to write down 32,000. And when I look at that 1,000, it says it's the volume. The volume is 32,000. So I'm going to need an equation that uses that 32,000. So when I look, what's my volume? Well, volume of a cube is this length times width times height. So x times h. That's going to give me x squared h. So now I have my helper equation. Right? I've got the equation I'm going to take the derivative of, and then I have my helper equation. Now, as far as solving goes, I always like dealing with x's, and even if I didn't like dealing with x's, I'm dealing with, it's easier to get the h by itself as opposed to getting the x by itself. So when I solve for h is equal to 32,000 all over x squared, and now I can plug this in here. And so now I get my new function. And here, I don't need the words anymore. So surface area is equal to x squared plus 4x. But instead of h, I've got to write down what h equals, which is this thing. 32,000 all over x squared. And now everything's one variable, but I want to clean it up before I start doing any calculus, so I end up with x squared. Let's see, the x's cancel, so I'll get, I think that's 144 with some zeros. And that technically it would be over x, but I'm going to write that as x to the negative 1. Did I do that right? Yeah. No, I did not do that right.
Isn't it
128.
28?
Yeah. It's like, well, I don't know what I'm thinking here. All right, 128 x to the negative 1. All right. Here, let me just write that whole thing. Thank you all for being awake. 128,000 x to the negative 1. Now I've got my surface area, so I can do my calculus stuff, which means take the derivative. I get 2x minus 128,000 x to the negative 2. That's 2x minus 128,000 over x squared. I'm going to find out where that equals 0. So let's see, 2x equals 128, a bunch of zeros over x squared. End up with x cubed is equal to 64,000. That actually works out nicely. Take the cube root of that. And so x is equal to 40. So if you were wondering, why on earth would anyone pick 32,000? Seems like a very strange number to pick, large, strange number. They picked 32,000 up here so that we end up with a nice answer here. If they just randomly pick some number for the volume, you get something hideous down here that you'd have to work with. All right, great. We found it was a flat spot. But that's not enough. We're looking to want to make sure that this is a minimum. So at this stage, I want to look at the second derivative. And so when I look at the second derivative, that's going to give me 2 plus 1, 2 plus 256, and some zeros, x to the negative 3. So our second derivative is going to be 2 plus 256,000 over x cubed. And when I plug 40 into this, I don't care what the number is, but I think we can all agree it's got to be positive. So this has got to be some positive number, and so here's what I know. I've got a flat spot and a happy face, and so that guarantees this is a minimum. But it's a minimum, is it the minimum, right? How do I know what else is going on? So I need to look at the domain. As far as the domain of this, if this is kind of if this is our restriction, our domain, well, the smallest x is ever going to be a 0. And unfortunately, the biggest x can be, in theory, you can have x go off to infinity. But what we know is we only have one critical value. And since we only have one critical value and we have shown that that one critical value is a minimum, then that has to be the absolute minimum. And I think